So one of the most important concepts in rotational motion is an acceleration that happens towards the center, and it's called centripetal acceleration. Okay. To understand this best, we'll be considering an object which moves with uniform speed in a circle. Okay, that means its angular speed is uniform, but it's changing direction all the time. The linear velocity changes direction. Yeah? Whenever there's a change in direction, that means there's some acceleration. Yes? Because we need any change in velocity with time produces an acceleration. So hence, there is always an acceleration in circular motion, even if the speed is constant. So say I'm doing a turn, 360-degree turn at 30 miles per hour, and I never change my speed. I keep it at 30 miles per hour. I am still accelerating towards the center because my direction is constantly changing. Okay? So if you go back and look at when we talked about linear acceleration, we said acceleration is rate of change of velocity, and that can happen in two ways. You can have change of direction or change of magnitude, or of course a combination of the two. Yeah? So in this case, we're looking at that change in direction, okay, which produces an acceleration. And if you have a change in speed as well, you will have a linear acceleration as well, okay, an additional acceleration. So this acceleration is due to the change in direction of the velocity, and it's called an centripetal acceleration because the direction of it is always towards that center, which is on the axis of rotation. Okay, O. So it's along this black line, which is marked as R, along the radius at any point. At any point, if you draw the radial line, it's along that radial line pointing towards the center. So if you consider two positions on this circle, here's a car going around in a circle, and let's say it goes from a position A to a position B. Okay, both are on the same radius away from axis of rotation. Let's say it's a perfect circle. So these two lengths are both R, and let's say it changes by some angle delta theta. So that's its displacement, angular displacement. These red arrows here represent its linear velocity. Since we said it's uniform in magnitude, so the length of the two arrows is the same, but you can clearly see that the directions are different. So if we want that change, we're going to have to take this final vector, pick this vector up, put it still here, right? And then we get our resultant vector by subtracting one from the other. So this direction would be our, I'm going to just roughly draw it for you. And remember, this is a very rough sketch just to give you an idea. So if we pick that vector up, we're going to go parallel to that vector, and I'm going to do this freehand, so I'm not going to be too good at it. Let's take a straight line. But something like this would be my vector VI, yeah? And I want to go opposite direction, so that means I need to go in this direction by the equal amount, yeah? And then the resultant vector would be joining my initial and final positions, yeah? So we're going to see something like that vector subtraction on the next slide to get the direction, yeah? And that direction you will see comes out to be pointing towards the center. So here are my vectors. We pick them up. This is VF. This is VI. It would have been pointing that way. We do its negative pointing this way. Its delta V is pointing downwards, which is going to be actually pointing exactly towards the center. Okay? So since these two are at different positions, if you take an average here, vertically downward is going to be pointing straight down to the origin. And that magnitude of, so that's the direction towards the center always of centripetal acceleration. It's a vector quantity. What's its magnitude? Its magnitude is V squared over R. This is not too difficult to derive, but we do not need to derive it in this course. So we're just going to take it as a given. AC stands for centripetal acceleration. Its magnitude is V squared over R, where V is our linear velocity. Yeah? Okay, so that's that uniform value of V, the length of this arrow, that respectively in meters per second. Yeah? Okay. Now, since we know the relationship between linear and angular quantities related through this r, we can replace v by r omega. So if we have a equals v squared over r, or r squared omega squared by making that substitution, one of the r's cancels out to leave us r omega squared. This is another way of expressing centripetal acceleration in terms of angular velocity. Yeah? Okay. So if you had a tangential component, if say you did not have a constant uniform speed, but a changing speed, that means our red arrows were of different lengths, then you would have a tangential acceleration due to that change in speed, and a centripetal acceleration due to the change in direction. And so your resultant acceleration would be given by this Pythagorean theorem for the right triangle. Let's just go back and see that. So this is tangential acceleration squared plus centripetal acceleration squared. The square root of the whole gives you your magnitude of your overall total acceleration. So I need to go back. So my tangential acceleration is always perpendicular to the radius because it's a tangent, right? And so it would be in the same direction as this red arrow along that line, tangent. And the centripetal would always be radial. So they're always perpendicular to each other. Tangent and radius on a circle are always perpendicular to each other. So these would be your two axes, yeah? X and Y. Hence the Pythagorean theorem applies because we have a right triangle. Okay. Most cases you will get only change in direction to deal with, and you'll have a uniform velocity, but you might get cases where you have non-uniform speed, in which case you need to remember to get your total acceleration by combining your tangential and centripetal accelerations. Okay. So we talked about the direction of omega earlier. One way to find the direction of omega is to grip your axis of rotation with your right hand, and when your fingers are pointing in the direction of rotation. So here, this is my direction of rotation, okay? And the fingers are pointing exactly the same way as though they were rotating. Then your thumb will automatically show you the direction of omega, okay? So omega is always perpendicular to the angular motion. Okay. I want you to try that on this diagram and this diagram with your right hand. You cannot exchange your right for your left. You want to just curve your fingers in the direction of rotation. Notice which way your thumb is pointing. It should be pointing in the direction of the red arrow. Do it for the lower one. You're going to have to point your hand down and do that. Okay. So if, just like in the linear case, if your angular acceleration and your angular velocity are in the same direction, be they clockwise or counterclockwise, then the object is speeding up, right? And if they are in opposite directions, one is positive, one is negative, or one is clockwise, one is counterclockwise, then your object is going to be slowing down. Exactly the way it was in linear motion. Do you remember we are looking at velocity arrows and acceleration arrows? And if they're both in the same direction, then your object is speeding up. If they are in opposing directions, your object is slowing down. Okay? So centripetal force needs to be provided by something. Unlike most forces which exist and we just label them, this is a force that doesn't exist on its own. Something has to provide that centripetal force, otherwise your object will not go in a circle. Okay, let's understand this better in terms of Newton's first law of motion, that an object continues in its dead state of rest or uniform motion unless acted on by an external force. So if my object, say this puck, is, let's say it's attached to a string, and let's say you were holding the string. So you're rotating around an object, okay? That puck or a stone, which is tied by a thread. You might have done this sometimes as a child. And let's say the string snapped. What's going to happen to that puck? It's going to fly off at some angle. It's not going to continue in that circular motion. So which angle does it fly off? It flies off exactly, the direction of its velocity remains exactly the same as the minute it got snapped, the string got snapped. So it keeps that linear direction of the linear velocity, and it moves in a straight line that way, because suddenly now there is no external force which was being provided by the tug on this string or the tension in this string. Yeah? So this was the external force being applied in order to make sure that this puck travels in a circular motion, right? That force, remember, force is intimately related to acceleration, F equals m into a. That still applies, right? So this force is in this direction, the acceleration is in this direction, that's my centripetal acceleration, that's my centripetal force. Here, in this case, being provided by the tension in the string. The minute I cut off the tension in the string, my object is no longer moving in a circle, it flies off at whichever angle its linear velocity happened to be at, yeah? At the minute you cut off the string. Okay, let's look at some other examples for what provides centripetal acceleration and centripetal force. So the magnitude of that centripetal force, okay, F equals m into a. We already know a is v squared over r. We just need to multiply by the mass of the object. So now we have centripetal force being given by mv squared over r. So if you do not have a centripetal force, you do not have circular motion. Okay, they go completely hand in hand. So some physical force has to provide that centripetal force. If you imagine a car turning on a circle, like roundabout, okay, or it's taking a curve, it's the friction of the tires between the tire and the road that provides that centripetal force. So you might have heard that on icy mornings, they warned you to go slow on curves, yeah? Why is that? That's because the coefficient of friction has reduced, yeah? Ice has much lower friction with the tire than the road had, so your grip is worse. And so you can afford a much lower velocity for taking that curve, much lower speed. We know friction is mu times the normal force, okay? So mu times normal force equals mv squared over r to provide us sufficient centripetal force for this car to take the turn towards the left here, because that's the direction for the friction. So we can use this to get an estimate of our velocity if we know the mass of the car, the radius of the curvature, okay? So let's equate these two. We know the normal force is equal to mg because it balances that off. The car is staying on the level. It's not going up or down, okay? So the two m's cancel out. We have mu g, and we cross multiply with this r. Mu g r equals v squared. So the velocity with which you can take the curve safely and remain in the curve is given by g, which is fixed, mu, which is the coefficient of friction, times the radius of curvature of the curve. Yeah? So the bigger the curve, the faster you can go. The tighter the curve, the slower you have to go, okay? Which makes sense. The smaller the r, the smaller the v, right? And if you lower the friction by having ice on the road, then you have to lower your velocity. Otherwise, you're no longer going in the circle, right? You'll go off in a straight line, your car will skid. And we have this experience. So you've understood skidding. Yeah? If you have a banked road, you can actually go a bit faster. And you might have seen this in car races where they bank the tracks quite steeply, in fact. So now our car is no longer level, it's going on this bank, and the bank is raised everywhere. So one tire is lower than the other. My normal reaction, remember, always has to be perpendicular to the surface. So my normal reaction is no longer upwards, it's perpendicular to the surface. The surface is inclined at some angle theta with respect to the horizontal ground, right? So my vertical is to that normal is the same angle theta as this. So I now need to resolve this normal force. N cosine theta, remember, because this side is adjacent to the angle. So n cosine theta will be along the vertical, which is here. And n sine theta will be along this horizontal direction this way, and sine theta. So I've resolved my vector n along this upward and horizontal directions. right? And the upward one has to balance mg, which is downwards, so that the car stays on this track. Yeah? It doesn't fly up from the track, doesn't try to go into the track. What about this force in this direction? This is going to provide our centripetal force. Yeah? So n sine theta up here, I wrote n cosine theta equals mg because these balance out. N sine theta is going to provide a centripetal force, which is mv squared over r. And now if I divide one by the other, we see these two ends are going to cancel out. Sine over cosine gives me tan. Tan theta equals mv squared over r divided by mg. And if we cancel the ends, tan theta equals v squared over rg. Yeah? Or v squared over r is centripetal acceleration. So g tan theta is going to give me centripetal acceleration. Okay? That means my acceleration now is greater than g, or is g times the tangent of the angle. So it depends on that angle. Yeah? And the velocity with which you take the curve is rg times theta, tan theta. Tan theta can be greater than 1, 2. Yeah? So it allows for higher speeds. Okay, let's do a problem on this. A rope tied to the end of a string moves in a circle at a constant speed of 2.5 meters per second and experiences an acceleration of 4 meters per second squared. What is the radius of the circle of its motion? So straightforward application of a formula of centripetal acceleration, A, now write that down, C, equals v squared over r, right? You are given A, you're given v, you just need to find the r. So you're going to substitute in the values, and you should get the same results as me. So compare your results to this, 1.56 meters, okay?